So just a reminder, our next exam is not this Friday, but it's next Friday, and that material that's on that exam covers up to what we're doing today. So anything after this that has thermal effects of flow reactors will not be on the exam. Yeah? Okay, go by whatever the syllabus says. Maybe I didn't have the right date on the syllabus. At any rate, it's not on Friday. Can somebody verify while I'm talking and then just raise your hand? Yeah?
Wait, so the midterm is not the 15th?
It's whatever, what's it say on the syllabus?
15th.
15th, then the midterm is on the 15th. If my day is wrong, then it should be whatever the syllabus says. So let's talk about this concentration term. We already saw that it can be a little bit tricky in a batch reactor. There's not much to derive in terms of a flow reactor if that flow is liquid phase. If the flow is liquid phase, then the volume is always constant. What do we mean when we say volume? There's two kinds of volumes that we can talk about inside of our reactor. When we were dealing with a batch reactor, generally that volume was fixed. Specifically, though, the volume we were talking about was the volume of the fluid that was reacting, right? We technically had a control volume inside there. Fortunately, for most of our batch reactors, the control volume was the same as the volume of the reactor. There wasn't any kind of a difference. When we deal with a flow reactor, which is our tube, right now the volume that we dealt with before is still a control volume element, but it's a little element delta V. It's that control volume element, I suppose you could imagine it as fixed, but we're letting the control volume element go to an infinitely small size. So we don't really talk about the volume of the control elements on here. The volume of the reactor we're talking about is the total volume of the reactor, right? As it goes from essentially zero volume, which is you entered the reactor, up to whatever the total volume of the reactor is. This particular volume doesn't come up very often. So whereas in the batch reactor we were able to say that the concentration of any species is equal to the moles of that species divided by the volume of the reactor, that definition doesn't really make a lot of sense when we're dealing with a flow reactor because the concentrations inside the reactor are going to change as you go down the length of the reactor. So it doesn't make a lot of sense over here to define the concentration of any species I as the moles of I at some location divided by the volume of the reactor. This definition doesn't make a lot of sense because that would only be the concentration coming out of the reactor. Instead, we modify that definition of concentration a little bit because we are dealing with a flow system. And so the concentration of any species I is equal to the flow rate of I, the molar flow rate of I, divided by little v. So the molar flow rate has units of something like moles per second, and the volumetric flow rate down here has something like liters per second, right? So that we end up with still a concentration unit, but it looks like moles per liter. The challenge that we have now is that this volumetric flow rate frequently changes as you go down the length of a reactor. The reason being, particularly for gases, if things are heating up, then the gas is expanding. And it is free to expand, right? There's nothing inside that reactor that's going to stop it. Remember, the reactor is just a tube. So maybe the gas can't expand this way inside the tube against the walls of the tube, but it's free to expand along the length of the tube. There's no reason that it can't do that. So we have to figure out why, or more specifically, how that V changes. The easiest case, which is case 1, case 1 is for a liquid, and for a liquid, little v is constant. Because for the most part, even if you heat up a liquid or cool it down or apply pressure or reduce the pressure on a liquid, it's always got roughly the same volume. So if v is constant, little v is constant, it also happens to be equal to the inlet volumetric flow rate, which is nice. If you have a liquid system, life is a little bit easier, and C sub I, therefore, can be equal to the molar flow rate divided by little v, or the molar flow rate divided by v 0, V0 being the entry molar, or entry volumetric flow rate. It doesn't matter, you can pick either one. For the gas flow rate, we're always going to use the ideal gas law. So when we go to use the ideal gas law, we're going to use it the same way that we did for the batch reactor, except instead of using volume, capital V, like we did up there on the left, we're going to use a volumetric flow rate and a molar flow rate, like we have over here on the right. So the ideal gas law, remember the general form is PV equals nRT, but we're dealing with a flow system, so this isn't going to be volume and that's not going to be moles. Instead, it's going to be P times the molar flow rate, or sorry, volumetric flow rate. Volumetric flow rate, little v, times the molar flow rate, F, R, T. What's the subscript that should go on F? Is it of the species or the total? It's a total, right? There's no way that we can split apart, well, I mean, I guess we could split it apart. We never talk about the volumetric flow rate as anything other than the total volumetric flow rate. There's no sub-portion of that volumetric flow rate that is species A and another part is species B. Similarly, when we were talking about the volume of a batch reactor, that's always the total volume of the batch reactor, right? You can't isolate the species and say such and such a percentage of that volume is to A and such a percentage is to B. So whenever you see this expression, that's always the total molar flow rate. So everything going in there. And just like we saw with the batch reactor, we're going to divide that by the initial values. Right, so P is the pressure wherever you are, P naught is the inlet pressure, Ft is the total molar flow rate anywhere inside the reactor, Ft naught is at the inlet, and similarly with T and T naught. One's anywhere and one is at the inlet. So ever so nicely, the R's always cancel. I'm going to have to go over to the next page. And what we end up getting is that V is equal to V naught times a bunch of quantities, which you should be able to show just by rearranging that ideal gas law, assuming that I did my algebra right, which is not always a given. T over T naught. Right, that's the form that we use for gases. So this is V for gases in either a plug flow reactor or a packed bed reactor. There is another kind of reactor that we haven't introduced yet, the stirred tank reactor that I briefly mentioned on Monday. We usually don't need this for a stirred tank reactor because stirred tank reactors are almost always liquid. We also haven't introduced stirred tank reactors, so who cares? This is also the form that you will use for one or more than one reaction. You can always use this form. It doesn't matter how many reactions are going on, you just have to sum up all the molar flow rates. If you happen to have a single reaction, remember that the total molar flow rate is equal to the initial molar flow rate, Ft naught, plus delta times Fa naught times X sub A. Right, this should look very similar to the total number of moles is equal to the initial number of moles plus delta Na naught times Xa. Right, they're equivalent statements, except one is talking about flow and one is talking about batch. You can put that equation into our expression for the volumetric flow rate. If you have a single reaction, then you can get what initially looks like to me a more complicated form, and yet this is the one that gets used a lot. 1 plus Ya naught delta Xa times those two ratios, P naught over P and T over T naught. Please keep an eye on my subscripts for the P naught and the P and the T and the T naught. I am known to flip those sometimes. Not on I'm not trying to trick you, I just flip them sometimes. So this is the version that we would use if we only had one reaction. There's no reason you have to use that version if you have one reaction. You can always use the one up at the top and get the same answer. A little bit of nomenclature that your book likes to use. I don't know why. This, and it has to do with a Y. I'm so funny. YA naught times delta is sometimes called epsilon. So your book will write that as 1 plus epsilon times x. There's no magic or mystery to epsilon. It's just the product YA naught times delta. And that's it. So either one of those. I tend to use the one on the top unless I'm trying to do something analytically so that I can actually get an X in there. Most of the time, if you're coding something, for example, in MATLAB, the one on the top is probably the easier one to code because you just have to sum up the flow rates, as opposed to this one where you now have to define YA naught delta and X. But you can certainly use either one as long as you've got one reaction. So that means the general form that we have, nope, not green, any C sub I is going to be equal to CA naught times theta I plus nu sub I times XA. As soon as you see the X, that should be a big flag that says this is only good for a single reaction. Over 1 plus epsilon times X sub A times those two pressure and temperature terms. T over T naught. Right, that's the general form. Actually, we saw a form just like that for a batch reactor. It looks the same here, except we've made use of that definition where instead of concentration being moles per volume, it's now molar flow rate per volumetric flow rate. So that time dimension got canceled out within that expression. So that's the general form that we would use, again, only if you have one reaction. If you have more than one reaction, you're kind of stuck calculating the molar flow rate of each species and dividing it by that V term up there. So I'll put that next to it. If you have the molar flow rates, or sorry, if you have multiple reactions, then you would do the molar flow rates divided by V naught times all that junk. So FT over FT naught, P naught over P, and T over T naught. You're kind of stuck using this form if you have multiple reactions. So this is more than one reaction, and this is one reaction. That's it. That's the whole discussion on concentration. So if you have a liquid, V is equal to V naught. If you have a gas, always use this form. If you happen to have one reaction, you can simplify this form with a gas phase. Well, simplify. Express it in terms of X if you want to. But again, you don't have to express it in terms of X. You can always use this one. Any questions on those equations? Yeah?
If we're dealing with a gas and the gas is expanding downstream, is the flow rate of the gas also changing as we go down the tube?
Yes, the volumetric flow rate is changing.
Okay.
That's what this term represents. Any other questions?
Does that mean that F is the molar flow rate?
Yes. So that also accounts for, well, if I had one molecule and I broke it in half, now I have two molecules, so presumably those take up more space than they did a moment ago, and that's going to accelerate everything and make it go a little bit faster. Cool. Okay, let's talk about pressure. Some of these terms are pretty easy to deal with, and you've seen the terminology before. Some of the terminology that we've seen is isothermal. So if we're talking about an isothermal reactor, all that means is T over T naught is 1. Right? The inlet temperature is the same as the outlet temperature. If we're talking about an isobaric system, that should be another one that sounds familiar. Isobaric is P naught over P is equal to 1. And then the last one, I can't really think of a word for this. If delta is equal to 0, if you're not changing the number of moles that you're producing in your reaction, then Ft over Ft naught is also equal to 1. So those are some quick ways. If you see those keywords, you can quickly simplify that concentration term or the volumetric flow rate term, because some of those terms are going to go to 1. So A and C these two generally come from the problem statement, or maybe they come from a reactor specification. Right, you don't really have a choice on C. That comes from your model. Whatever reactions you assume are proceeding inside your reactor, that's going to dictate whether or not delta is equal to 0. Whether or not the reactor is isothermal depends on how the reactor was designed, if you're actually out working on it. Or if I just tell you the reactor is isothermal, then you can get specification A. It's specification B that is a little bit trickier, because when we start dealing with flow systems, sometimes the pressure effects are always there and they're always important, even if we don't actually state them in a problem statement. And so the isobaric assumption, which we'll start talking about in blue, this one, there's one of two ways that you can do this. So let's call this B-1. It would have been easier if I had done 1, 2, 3 and then backwards. Anyway, isobaric always occurs when you have liquids. So if you ever see that your reactor is operating with liquid reactants, which again, we're never going to deal with phase changes. So if it starts out liquid, it's always liquid. If you are dealing with a liquid, then that system is always isobaric. The pressure will never change. The other option for B2 is if you have a gas, and here the pressure drop is potentially very important. Why is it important sometimes and other times it's not? It depends on the style of the reactor that you have. So the plug flow reactor is generally a tube, right? There's nothing special inside there, or a pipe, or whatever you want. There's nothing on the walls for the most part. And so the gases are relatively free to just move down the length of the reactor without being inhibited by any drag they experience on the surface of the walls. Normally in a plug flow reactor, we don't pay attention to pressure effects going down the length of the reactor unless your reactor is really old. If your reactor is really old, stuff can build up on the walls. So when you saw that catalytic converter that I handed around yesterday, those were really tiny channels. You can imagine if a piece of soot or something, or an unburned hydrocarbon from your engine, were to get in there and lodge itself onto one of those walls, that's a pretty big obstruction for any gases going through that individual section. It can also be quite a problem if you have a bigger reactor, because bigger stuff will build up on the walls of your reactor. So this is a piece of what's called slag that was chipped off the inside of a reactor that was being used, I think, to break down hydrocarbons. You have to talk to Dr. Hertz. But it looks like a chunk of coal. And this was built up on the reactor. I think he said it was something like 6 inches of coal that had built up on the inside of the reactor. It just sits there and deposits over time. This is a pretty significant chunk, right? If that's sitting inside the reactor, you've actually reduced the diameter quite a bit, which could also change all of that. But now it's kind of lumpy, right? And that's going to generally act to drag those molecules that are moving past it a little bit more than if the wall was smooth. So everything generally tends to slow down if this is building up on the inside of your reactor. Since I don't know the chemical composition of this, and I probably shouldn't have just grabbed it, given that I don't know what it is, I will pass it around, but keep it in a jar, and maybe don't shake my hand after I leave, because I don't know what's on my hands right now. So,
research that are doing kind of like corrosion prevention methods for that reactor? I mean,
yeah, so usually the way that they fix a reactor like that is one of two things. Either you shut it down and you go in there and chip stuff off, which is kind of a pain in the neck, but that could be the best way to do it. The other version is what's called regeneration. So when things get dirty like that, we call it either fouling or poisoning. And sometimes you can either flip the way that the temperature profile is going and slowly etch away at it, or you can introduce a different set of reactants that are designed to clean that stuff out. Either one of those are various ways to do it.
as far as like procedures, I think we should be researching that because now we can use kind of like basically either materials or elements that are less corrosive or.
There's a great, if you're interested in that, there's a book that was just published, I think it was like 6 or 8 months ago, called Rust. Because a few universities around, at least the US, are starting what are called corrosion engineering programs. And they draw, so far they've been sort of like little, I don't know, growths on chemical engineering programs because so many of those concepts draw from chemical engineering. So that is, it's not the fastest in the world because corrosion takes a long time. But in terms of money, we spend a ridiculous amount of money fixing corrosion. And so a lot of programs are coming up on the ABET radar at this point to get qualified so that they can be called corrosion engineers. So it's ongoing. Yeah.
It would be corrosion control chemical engineering.
Yep, that's pretty much what it is. The first like 3 years of it is the same as any other chemical engineering program. What was I doing? Oh yeah, right. Plug flow reactor, plug flow reactors. Generally, you don't have to worry about pressure effects because the walls are assumed to be smooth. If your reactor is old and you're trying to actually represent what's happening inside your reactor, you may have to worry about it. For us, if we are dealing with a plug flow reactor, we're never going to worry about pressure drop. So when I mentioned at the beginning of the class, one of those key points was the P table. This is what I'm talking about. It's a flow chart. It will help you decide how to account for pressure. If you are dealing with a liquid, then you will always get P over P naught is equal to 1. Right? Every time. If you have a liquid, that's the case. If you're not dealing with a liquid, the next question you have to ask yourself is, what kind of reactor am I dealing with? If you have a plug flow reactor, for the purposes of this class, and of this class only, P over P naught is also going to be equal to 1. Again, cases where that may not be the situation is if you have an old reactor, a dirty reactor, or the walls of the reactor are somehow very textured. But generally speaking, no. If it's a PFR, we don't care about pressure. The next question that you have is, am I working on a homework or an exam? If you are working on a homework or an exam, you're going to get one of two situations. Either I'm going to tell you what the pressure is, or I'm going to tell you how the pressure varies along the length of the reactor. what kind of reactor must I be dealing with?
Not a batch.
Not a batch, and not a plug flow,
PBR.
PBR. So the only time that we deal with pressure effects in here is with a packed bed reactor. The reason we deal with a packed bed reactor, I showed you a rough schematic or a toy model of what a packed bed reactor looks like on Monday's class, right? It was a bunch of spheres inside a tube. Those spheres tend to block the flow of the fluid pretty effectively. They're also usually not spheres, and they're quite a bit smaller than what we would have seen in class. This little bullet-shaped thingy is another one of Dr. Hertz's, I'm going to hold that with 2 hands because I don't want to drop it, little demos, which is a bunch of different types of catalyst particles. And if you take a look at it, I should do one of those, like, estimate the number of particles, like gelatine or something for it. A few of them are spherical. Most of them are not. They're things like honeycombs or porous spheres or cylinders or hollow cylinders or something like that, all of which impact the pressure along the length of the reactor in different ways. And we need different ways to account for things like shape and how well it packs together. So I'm also going to pass this one around. In true engineering form, it's sealed with duct tape, so please don't pull that duct tape off because you're going to get a bunch of catalysts all over you. And please don't drop it because it's made out of glass. But those are typical shapes of catalyst particles that you would find inside a packed bed reactor. And they're usually packed about that densely too, which is, we call them dumped packings or random packings. That's because you literally dump them into the reactor and whatever shape they take that's the shape. So they tend to pack pretty closely together, which also influences whether or not the pressure drop is going to be significant. So if you are working on a homework or an exam, and you have a packed bed reactor, and you need to deal with pressure, that means I have given you an expression for how the pressure varies as you go down the reactor. That can come in one of 2 forms. The first form is that I will say pressure is some function. Actually, let's call it, have we used the lowercase f yet? No.
Fugacity.
Not cool bringing up thermo. No. Yes, that's true. It is fugacity. I will tell you that the pressure varies with the inlet pressure, maybe the temperature along the reactor, and the weight of the catalyst, W. Right, I will just give you some function. Maybe it's a quadratic or a linear or something like that. I will just provide you a function that you can use that will let you directly calculate the pressure anywhere that you are inside the reactor. The other version is I won't give you the pressure, I will give you what's called the pressure drop, which is how the pressure changes with respect to a change in weight. So when we say dP dW, that means as I move incrementally down the reactor, I have exposed the gas to incrementally more and more reactor catalyst weight, which is the W on here. And again, for this, I will give you another function. This time, let's see. Okay, G is gravity. No, I think we're good with G. The F and the G here are arbitrary functions. They're not anything that we've already been exposed to. But generally, this will also depend on one of those parameters. I am going to have to do one of my little tricks here of moving that up because I need a little space below it. There we go. So these are one of the 2 forms that we would generally classify as a packed bed reactor with pressure effects. That's the general terminology. If we say pressure effects or pressure drop or something like that, we're talking about functions like this that describe how the pressure inside the reactor changes as you go down the length of the reactor. They're usually not changing in time, right? If the reactor is the length of this room and I walk over 3 meters from the end and I look at the pressure here, that pressure is always constant. We're still dealing with steady state systems. But the pressure here is slightly different from the pressure a little bit further upstream. Right? It usually flow is driven by a pressure gradient, which flows from high pressure over there to low pressure over there. So these two terms are both describing how that pressure changes as you move down the length of the reactor. If you are not on a homework or an exam, what would you be working on that could require pressure that's not a homework or an exam? The project. The project form for a pressure drop follows a fairly standard, well, it's standard in the sense that everybody uses it, it's not particularly simple, form for the pressure drop called the Ergun equation. It is what's called an empirical equation, which means you cannot start from a material balance and energy balance and maybe entropy, since we're shooting ourselves in the foot with thermo. You cannot start from first principles and derive an expression like this. You have to go out and measure some values and figure out what some of these coefficients are. That also means that the units involved in empirical equations are usually fixed. Somebody went out and figured out what those numbers ought to be, and they have fixed units. You can't just throw around any sets of units that you want. I'm going to give you the equation here and roughly describe what each parameter means. You're going to have to do a little bit of learning on your own when you go to the project. I pointed you in the section of the book that discusses this equation, but you're going to have to figure out what those units are so that you can use them in your project. So this form, and it's written as dP dz, z meaning moving along the axial direction of the reactor. Your book will show you the way to convert from dP dz, which is pressure drop per length, to dP dW, which is pressure drop per unit of catalyst. What? I don't know. I didn't hear anything. All right, the way that this works is a rho on the bottom. The rho here is the density of the gas times G sub c. G sub c is the gravitational constant, times the diameter of the particle that you're dealing with. The diameter of the particle means the diameter of that little catalyst particle that's being passed around. But most of the time, or actually I shouldn't say most of the time, some of the time those catalyst particles are not spherical. So it's not always clear which particle diameter that we use here. There are different ways to estimate what's called the effective particle diameter. This equation that we're going to finish as soon as I stop blabbing was designed for spheres. There are ways that you can modify this d sub p parameter to account for a non-spherical shape. The project uses spheres, so we can just take the diameter of the sphere. Over G, I'm not going to tell you what big G is. You're going to have to look it up. It's a mass flow rate. Times a quantity 1 minus phi over phi. Phi is a parameter that we haven't seen before. Or sorry, phi squared. Where's the little catalyst thing that's being passed around? So inside that thing, let's consider it to be a cylinder, right? It looks like a glass cylinder and there's particles inside of it. The entire volume within that glass cylinder is just a quarter pi d squared times the length of the cylinder, right? It's that total volume inside it. The amount of volume taken up by the catalyst is necessarily less than that. If the catalyst took up the entire volume inside that cylinder, it would be a solid chunk of catalyst, and you can't get gas to generally go through solids at any appreciable rate. The phi parameter is what's called a packing factor. If phi is 1, then you have completely filled up that cylinder. There are no catalysts that exist that have phi of a value of 1. This is called a packing factor. And again, your book goes over what all these terms are in a little bit more detail. It's only about 3 pages, and you'll have to read that to do your project. But the phi parameter says if I were to dump this packing inside there, approximately what percentage of that original cylinder do I have is now filled up by catalyst, right? There's some proportion of that that's filled up, and that's what phi represents. These parts, all those terms were defined, actually, not excluding the phi, were defined from basically making the units match. If the units match, we needed something like that. These other terms are the ones that come from experiment. So there's no way to guess these forms. And if you look at different equations, they have different forms. So we have 150 times 1 minus phi times a new parameter we have that's mu. Mu is a viscosity. So if you have a very thick gas, right, it's very viscous, not honey viscous, because honey is a liquid. But if the gas is particularly viscous, and this number is very large, that will tend to make this pressure drop term higher, which means pressure gets lower as you go along the length of the reactor. And then the term in the denominator here is the diameter of the particle, plus 1.75 times this parameter g, where again g is related to the mass flow rate, but I'm going to let you look at the definition in the book to figure out how you relate it. And so this equation is called the Ergun equation, and that's the one that you're going to have to use on your project because it's a much more accurate depiction of how pressure actually changes as you go through a packed bed. But notice it's only good for a packed bed. There's another version that we would use if we actually needed to estimate the pressure drop in a plug flow reactor. And it's also an empirical relationship. So there is no way to derive an exact relationship like this and get all those numbers. Somebody went out and measured the pressure drop for a bunch of different spheres, for a bunch of different flow rates and stuff, and came up with that expression.
Professor, could you just write down the name of that equation?
Sure.
Thank you.
This is called the Ergun equation. There was a huge fight in fluid dynamics, like I think it was back in the early 90s, over whether this was 1.75 or 1.8. There were like papers published back and forth. It was the equivalent of like a scientific flame war as to whether or not it was 1.75 or 1.8. You will see it written both ways. Our book uses, we are the old guard, we assume it's 1.75. But that is called the Ergun equation. Actually, the plug flow reactor version, if you need to know the pressure drop inside a plug flow reactors are basically pipes. And when you take 101A, you'll figure out how pressure changes as you go down a pipe. So you'll get the more exact version of a plug flow reactor in 101A. 101A doesn't go into the Ergun equation. But we do. So hold on to this table. That will tell you what to do. There is one other, I guess, possibility here. What else could the pressure drop be on a homework or an exam?
Constant?
Could be isobaric, right? I mean, I could give you one of these functions, but maybe the function is p is equal to p naught, which is an isobaric system. So it's always possible that I could tell you to ignore pressure in a packed bed reactor, but that's sort of a special case of that top equation. Any questions on how to use the table? Where to go? Don't kill yourself trying to memorize that one because you're only going to use it on the project. And the book does a pretty good job of giving you some examples of this. Yeah?
In that equation, what is phi again?
Sorry?
Phi.
This parameter? Yeah. This says if I have a particular volume, let's say the volume of this room, if I tried to fill up this room with soccer balls, the volume of soccer balls is not the same as the volume of the room, right? It's a little bit less because I can't pack them perfectly inside here. I can't fit a sphere inside of a rectangle. This phi is saying what's that ratio of the volume of stuff I actually fit in there to the total volume that I could have used.
So like how is the that goes?
It has to be given to you. I mean, or you have to go measure it, right? You have to figure out what your shape looks like and dump it into something and figure that out. You can estimate them if the geometries are simple. For example, spheres, we can solve those numbers exactly for a sphere. But we have what's called random packing, right? When somebody is packing up a cylinder or something like that with spheres, they're not setting each sphere individually to get that maximum packing. They've got a bag and they're dumping the bag in there. So even a theoretical estimate is usually not what it actually is. But at the end of the day, it's a measured value. It has to be given to you somehow. Any other questions? Yeah.
So even though our exam is going to be on Monday, is this still the last day of material for that exam?
Yes.
Okay.
There will be no thermal effects of flow reactors. Although, as we will see on Friday's class, the equation of change for temperature, the energy balance for a flow reactor, is almost identical to what it was for a batch reactor, but it's still not going to be. All right, I'm going to start an example. We probably won't have time to finish it today, so we'll finish it up on Friday's class, just to see, what does a plug flow reactor or a packed bed reactor problem look like in terms of the problem statement, and generally the solution. I've oversimplified this statement a little bit just so that we can make progress on the actual reactor. So here's our example. Nice simple reactor, doesn't even have the fancy end caps on it. The reaction that occurs inside the reactor is A goes to B. We have some inlet and some outlet. The inlet is going in at a volumetric flow rate of 1 liter per second. The reactor itself is a packed bed reactor. And we know a little bit about what's happening inside that reactor. First, it's filled up with a catalyst such that the density of the bed, which, by the way, the density of the bed, the packing factor, and the solid density of the catalyst are all related. So you'll probably have to use that on your project. The density of the bed is 2 kilograms per liter. So remember, technically the units on this are, actually let me change that color on there. Kilograms of catalyst per liter of reactor. We usually don't write those units all the way out. We usually don't say kg cat per liter reactor. We just say kg per liter. But they are talking about two subtly different things. Remember when I mentioned that density of a bed, it's not quite the same density we've been exposed to previously, like density of water, where it really is mass of water divided by volume of water. It's slightly different here. The reactor is also going to be isothermal, since we haven't dealt with the energy balance yet. What else did I say? The reaction rate constant is 0.1 per second, and the amount of catalyst that we have in there is 100 kilograms. If I don't tell you the amount of catalyst that goes into a packed bed reactor, that's equivalent of telling you not telling you how long to run a batch reactor. Right? If I say run a batch reactor and plot temperature as a function of time, I don't need to tell you what the quote-unquote final time is to run that batch reactor. Similarly here, if I tell you to plot the temperature, or let's say flow rate, since we're not doing temperature yet, flow rate as a function of catalyst weight, I don't have to tell you that there's 100 kilograms inside the reactor. You can just plot it for any number of W that you think is reasonable. It's equivalent to not specifying a time. But here I've said that the reactor contains 100 kilograms of catalyst, which is like saying run the batch reactor for 100 seconds or something like that. And so for this example, we want to do two parts. One, let's get the conversion as a function of W if P over P naught is equal to 1. The other version that we'll do is to get the same conversion, X as a function of W, if, and this is one of the ways that I can tell you what the pressure is, the pressure is equal to the initial pressure times 1 minus 0.003 W raised to the 1/2 power. Generally, when you see an expression like that, you're going to see exponents that aren't integers, which when you get to 101A, you'll roughly figure out why those things are never integers. So a little note here, by the way, this is an elementary reaction. What is the rate of consumption of A? Sorry, what are the rates? Yeah, sure. What's the rate? KCA. What are the units of R sub A? Mole per liter per second. Our equation, though, if you flip back to yesterday's class, needs an RA prime. What are the units of RA prime? It was moles per something per time. What was that other unit that was there? Because we're in a packed bed reactor. Mass of the catalyst. So we need a kg here. So if we just look at the way we need, sooner or later, we need to convert between these units and these units. The easiest way to do that, if we look at these units here, is if we could multiply this by a kg of catalyst per volume of reactor, we would then end up with units that look like this. Right, so this conversion factor that I think we briefly brought up on Monday's class is what? The bed density, this bed over here. That's telling you there's so and so, such and such an amount of catalyst, kilograms of catalyst, per volume of a reactor. So if we want to convert between these two, the conversion is that R sub A is equal to rho sub bed times RA prime. The reason that we need that pretty frequently is because we're used to writing these elementary rates in terms of a per volume basis. But pay attention to whatever the units are of K, because occasionally K will have the correct units on it of mass already. But if it doesn't, if you find out, oh, it's got moles per volume per time, you need to use this conversion factor. There's no general way to approach that other than check the units. If the units aren't right, then you got to switch over to using that. That's time, yes? Yeah. So we'll finish up this example on Friday and briefly introduce the energy balance. Thank you all.